for coming. My name is Stuart Marks. I work in the core libraries team in the Java platform group at Oracle. I work on Java and the JDK. And one of the things I work on is the collections framework. So the talk today is collections refueled. And so collections has a long history. I'm going to do a very, very brief history of that. I am going to spend some time talking about Java 8, even though Java 8 has been out for almost 3 years now. There are some interesting features that were added to collections in Java 8 that don't seem to get enough publicity, so I'm going to talk about those a little bit, and then move on to some new features in Java 9. So there's a Twitter hashtag, collections refueled. You can see that up at the upper right. So if you want to tweet to me during or after the presentation, I will look at that hashtag and respond to any questions there. Or it's a small crowd. If I have time, we can take questions at the end. And I'll be around the conference for the rest of the afternoon as well. All right, so history of collections. So Java is now over 20 years old. And the collections framework is not quite as old as Java. It is almost 20 years old. The Java 1.0 was introduced with what we now call the legacy collections. So there was no collections framework in the very beginning. There were the old things, vector and hash table, or hashtable, as some of us call it. But those were replaced in JDK 1.2, and that's the collection framework that we're all familiar with the interfaces, collection, list, set, map, and so forth, and the concrete classes to back them up. The usual suspects, array list, hash map, hash set, and so forth. So those were introduced in 1998, and so that was 19 years ago. And so those are in use daily. In fact, a paper just came out a few weeks ago, or no, actually it was pre-published. It's going to be published at the conference this summer, I think. Basically did an empirical study of the usage of collections. And it turns out ArrayList, surprise, surprise, is the most used collection in Java. Some very large fraction, might have even been a majority of uses of collections, are ArrayLists. So moving on quickly, in Java 5 in 2004, generics were added to the language, and that had a huge impact on the collections APIs. And so by now, I hope everybody is converted over to using genericized collections instead of the original raw collections. And the other big addition in Java 5 was the addition of the concurrent collections. I'm not going to be talking about those today, but that's a whole kind of related framework that has some overlap with the collections framework. And then along the way, various individual implementations were added in various releases, such as ArrayDec, Priority Queue, EnumMap, EnumSet, and so forth. So those are very specialized collections. They don't get much general use, but when you need them, they're there, and they are really useful. All right, so Java 8 collections enhancements. So I think most people are aware that the big features of Java 8 were lambdas were added to the programming language, and the Streams API was added to the core libraries. So, really interesting feature, really useful. I hope everybody's using them. But backing them up are some additional language features. In particular, interfaces can now have default methods and static methods. So that's an interesting language feature. I'm not going to talk about the language enhancements themselves. What I do want to talk about is the way we use those language features in the JDK to enhance the collection framework in JDK 8. And so what we did was, for the first time, I say the first time ever in 15 years, I think for the first time ever, we actually added methods to the collections interfaces. And so that was the big deal about default methods. Prior to default methods, you could not compatibly add methods to an interface. Otherwise, it would be an incompatibility. So in Java 8, with the addition of default methods, it's now possible to add methods to interfaces, and we went ahead and did so. And so collection, let's see, iterable collection list got a few new methods. Map and comparator I'm going to spend a little more time on because they got quite a number of new methods. And the interesting thing about this well, a bunch of interesting things. Those new methods were, I mean, it's not a requirement that new methods have to use lambda, but a lot of those new methods were added from the standpoint of, oh, now that we have this new method, when that new method can accept a lambda, it can do many more powerful things. So I have a bunch of examples of that, and, starting, in fact, on the next slide. So the iterable interface has been there since Java 5, but basically it allows you to use the enhanced for loop. So in Java 7 here, I have kind of pairs of code snippets. On the top, there's Java 7, and then down below a rewrite of that in Java 8. And so in Java 7, if you wanted to iterate over a list, you could use officially it's called the enhanced for loop. Some people call it the for each loop. I tend to avoid calling it that because there's now a method called for each. And so in Java 7, you write the enhanced for loop. But in Java 8, what you can do is call the for each method and pass it a lambda. And what it does is it executes that lambda on each element in that list. And so that's a little syntactic nicety. But iterable is inherited by every collection implementation. So all the collections are now enhanced by having this for each method on them. And in fact, indeed, all the other default methods are inherited all the way down the hierarchy. So what we've done is, by adding default methods, we have enhanced every existing collection, even ones that were not introduced in Java 8. All right, continuing on the iterable, actually this is iterator, not iterable. But if you've ever written an iterator, you had to write a hasNext method and a next method, and oh, that's right, you have to also write the remove method. Well, I don't want to support removal, so you always wrote throw new unsupported operation exception. And so now there's a default method on iterator called remove. There's a default implementation which simply throws unsupported operation exception. So this is really nothing more than a convenience. If you're writing your own iterator, you simply, if you don't override remove, well, you don't have to override remove anymore, and if you don't, you get the default behavior, which is to throw an exception, which is pretty often what you want, because there are relatively few iterators support removal. But if you do want to support removal in your iterator, you just go ahead and override it like you always did. All right, now things are getting a little more interesting here, because instead of just sort of syntactic niceties, we're getting into some bulk operations. So suppose you have a case where you want to run through a list and remove elements that match some criterion. So in Java 7, you had to write the for loop. You had to write it out kind of the old way by using an iterator. So a key point here is that you cannot use the enhanced for loop because you can't remove things from within a loop, otherwise you will get a concurrent modification exception. And so what you had to do was fall back to the original loop using an iterator, and then if something matched, you called remove on the iterator. So that's the Java 7 code. And it's kind of bulky, especially, even compared to the enhanced for code, the enhanced for loop code that you would write if you weren't removing something. Now in Java 8, there's a new method, RemoveIf, that takes a predicate. And the semantics are that predicate is applied to each element of that collection, and if the predicate returns true, then it removes it from the collection. And so that's pretty nice. I mean, so you look that 4 or 5 line for loop there collapsed down to a single line. Makes things much nicer. But it's not only a syntactic advantage, it's actually a performance advantage. And so if you consider iterating over an array list, if you remove something from an array list, it has to shift all the elements up in place. And so if you do that repeatedly within an array list, then you get an order n squared performance because it's repeatedly shifting the tail of the array list back up as elements are deleted. And so RemoveIf in Java 8 is optimized for array list. What it does is it keeps track of which things are removed and then does the copy-in operation all at once. And so we've reduced the algorithm from n squared to order n. At the same time, we've made the code a lot more concise. And so the benefit here is that the RemoveIf operation, it's internal iteration, and It's raised the semantic level of the API. So instead of looking at the collection from the outside and picking at things one at a time, we're now saying, okay, remove all the elements, remove all the matching elements. That's basically what this says. And so the implementation takes advantage of that with a better algorithm. All right, moving on, more new default methods. The list interface has a couple new methods on it. One of them is ReplaceAll. And so what that does is it replaces every element in the list with something else. So suppose you wanted to do that in Java 7. Again, you could use the old-fashioned or the original style of for loop using a list iterator. And then the example here is, suppose you wanted to run through a list of strings and convert them all to uppercase. So you could run a list iterator over the list and set each element to the element converted to uppercase. So that's the top code snippet there. But most people don't do that. Does anybody ever use list iterators? Any show of hands here? No, I think list iterator, I mean, it's interesting and powerful, but I think nobody uses it, and oh well. And the reason is, if you had different kinds of lists, then you would want to use an abstract way to iterate over them using list iterators. But since everybody is using an array list, you might as well just index into it. And so that's the second code block here. And I think everybody would probably write it this way, where you just index from 0 to size, and then set, just call set and get using the index operations. And that's perfectly fine if you know you're operating on an array list. If you're operating a linked list, then that will slow drastically, but you shouldn't be using linked list anyway. And that's a different talk. So anyway, in Java 8, this gets even better. So we just call the ReplaceAll method and give it a lambda function, or method reference in this case, that transforms the element. And so we say string : to uppercase, so that takes a string, converts it to uppercase, and ReplaceAll just runs through, for every element, replaces it with its uppercase equivalent. And so in one line, we've replaced those loops that kind of did things sort of one at a time. Now, when people see this, they'll often say, oh, I want to change this list so that every element is transformed into something different of a different type. And you cannot do that with ReplaceAll. For that, you need to use a stream. Stream out the elements, transform them into something of different type, and then collect them into a new list. All right, so another method that was added to the list interface is sort. So, well, big deal. Instead of calling collections.sort on a list, just call list.sort. What does that buy you? Well, a couple things. So the collections.sort method had to operate on a list of any implementation of list. And so the most generic way to do that is to copy out the list elements into an array, sort that, and it would be a temporary array that was temporarily allocated just for the purpose of sorting, sort the array in place, and then copy all those elements back. And so the default implementation of list.sort does exactly that, because it doesn't know who it's inherited by. However, ArrayList.sort, again, ArrayList being the most commonly used collection, ArrayList.sort overrides the default implementation and says, hey, I am an array list. I know I have all my elements stored in an internal array. I'll just sort them in place. In fact, there's something called arrays.sort. So all it does is turn around and call arrays.sort on its internal array. And so we've saved a bunch of memory allocation, and we've saved a copy out and a copy back in. So the override of ArrayList.sort actually is buying us quite a bit here. And in turn, collections.sort simply turns around and calls sort on the list that it's provided. So you don't even have to change your code. So if your code is using ArrayLists and you call collection.sort, you get this new behavior for free. All right, now moving on to map. There are a whole bunch of methods added to map, but and I'm going to run through, I think, some of the more interesting ones here, but there are a lot more than I can cover in this talk. So in Java 7, if you wanted to do something for every element of a map, like print out the key value, print out each key and value, you'd use you'd usually do a loop over the entry set of the map, and then do something useful within that for loop. And so in Java 8, there's a for each on a map. It's just kind of like the for each on Iterable, except that instead of taking a function that takes one argument, it takes a by function, which takes two arguments, the key and the value. And so you can write a lambda expression that does that, and it's mostly a syntactic nicety, but what it does is instead of you having to iterate over the map entries and then do get key and get value, it just hands you the key and value separately. So it's much more convenient in that way. Similar to list, there's also a ReplaceAll on map. And so again, you can in Java 7, you had to write a for loop over each entry. MapEntry has a set value method, so you can actually modify the underlying entry in place. But ReplaceAll does that for you. And so the semantics here are, this takes a lambda that takes two arguments, the key and the value, and the return value is the replacement value. And so if we want to change all of the values in the map to uppercase, we just write it here, kv arrow, and then call v.toUppercase. So this is kind of limited. I mean, if you want to do exactly this, it's wonderful. But it can only change the values in the map. You can't change keys, and you can't change the types of either the key or the value. So there are limitations there. If you want to do those things, you have to go over to streams and stream over the map entries and transform things that way. All right, now here is kind of an extended example. And I'm going to set this up by talking about multi-maps, which many people are familiar with. But if you have one of the things about the built-in map has key value pairs, but most importantly, for every key, there is exactly one value. And in many cases, you might want to have a data structure where you have a key that maps to multiple values. And so there are various libraries, such as Eclipse collections and Guava, have multi-map data structures built in. The JDK does not have one. And sometimes, if you can't use one of those libraries, what you have to do is say, okay, I can't use a multi-map, so instead I'll write out a map from, say, if I want a map from string to multiple integers, I would have a map from string to set of integers, and just store that in a regular hash map. And in Java 7 and earlier, this can actually get pretty painful. And so here's some code to do that. If I want to put a value, string and an integer, into my multi-map, then I first have to say, okay, get the value for the key to see if there's a set already there. If there isn't, then I have to create a set and put it into the map. And then, finally, after that, I have to add the new integer value into that set. There's a similar thing for removal, except kind of in reverse. I have to get the value corresponding to this key, and if it's non-null, then I go ahead and remove it from the set. Oh, but also, if the set now became empty, I want to remove the whole thing. And in fact, all right, I'm out of room on the slide, so the code is already too bulky. So it turns out there are a bunch of new methods in Java 8 that make doing things like this really easy. So one of them is compute if absent. What's interesting is that the concurrent hash map prior to Java 8 had some of these, because you really need atomic composite operations on a concurrent map. So some of these have been promoted to the main map interface in Java 8. Anyway, so compute if absent is an interesting thing here. What it does is it evaluates the lambda expression that you pass it if the key is absent. And then it takes the result of that and stores it in the map. And interestingly, regardless of whether it actually did that computation or not, it returns the value corresponding to the key. So you have to pick through this a little bit carefully, but basically what this does is add the new hash set if it's absent, and then we have a set-valued multimap, and so what the return from ComputeIf absent is the set of integers, and then we just go ahead and add it. And so I'm not going to go through all of these in detail, but you can kind of see they have the same flavor. Remove is kind of the same way. There's this kind of complicated expression there, but what remove can do is actually, so there's a dual to ComputeIf absent, which is ComputeIf present. And what these can do is, if the return value is null, it actually has the effect of removing a mapping from the map. And so if you run through a multi-map style collection, there are the usual map kind of operations, like I show put, remove, contain, size, values, and so forth. Basically, with the new default methods on map, all of these turn into one-liners. And so if you don't need to have a full multi-map implementation, and most applications don't, maybe you just put a bunch of stuff in and then say, okay, I want to deal with these particular cases. You can kind of get the effect of your own multi-map just by implementing a few of these one-liners. So in fact, this isn't even the half of it. So I showed ComputeIf absent, ComputeIf present, and getOrDefault, which are new methods, new default methods on map. There are, I think well, I'm not even going to go through them all. There are a bunch more. And what you have to do is go through the Java doc and look for things on the map interface that are since 1.8. But anyway, I think these are the most interesting ones here. All right, so there's another interface that we spent a lot of time on in Java 8, which is Comparator. Now, comparators are, in their simplest form, are pretty easy, but when they get complicated, they get really complicated and error-prone. And I think there's a whole other talk to be done about comparators themselves. But what we did in Java 8 was add a bunch of helper methods, or combinators, which construct simple comparators for you, and then also combine comparators to create new comparators that give more complex and interesting behavior. And so what that should allow you to do, and it's not quite there yet, but probably in a large fraction of cases, what these new methods allow you to do is take a bunch of hand-coded open logic and compress it into essentially successive calls to these comparator methods that provide composite functionality and make things much neater. All right, so I'm going to run through a quick example here, which is a two-level sort. So suppose you have, is it a person class? No, a student class or something like that. Just say student has a last name and a first name. So I want to do the first level sort on the student's last name. And then for students that have the same last name, I want to do a second level sort on the first name. But there's also a catch, because maybe we don't have maybe we don't have a first name for all the students, and the first name might be null. And so if the student's first name is null, then those should sort before all other students that have a non-null first name. All right, so let's look at what you have to do in Java 7 to do that. And I'm not going to pick through all this code, but you can kind of eyeball it and say, okay, we get the last name to compare it, and then, all right, so if the last names are equal, then we get the first names, then we do null test, and then, there's a little bit of dancing around here. And I'm pretty sure this code is correct, but I'm not entirely sure. You could pick through it, and in fact, if I introduced a bug, then it would be really hard to see that there actually was a bug, because there's lots of little conditionals in here, lots of little details. If you swap a 1 and a -1 in the wrong place, boy, it's really hard to determine that by inspection, unless what you do is you go out and get some sample data and pick through it or step through it in debugger or something like that. So this stuff, writing this kind of stuff is really error-prone. And I see a lot of questions on Stack Overflow and forums about what's wrong with my comparator and so forth. And it's not surprising, because this is it's really detailed, and if you don't get it exactly right, you have a subtle bug that can creep in. All right, so in Java 8, all right, so this is a little bit of a refactoring. So instead of calling collections.sort, we call students.sort, and instead of using an anonymous inner class, we convert it to a lambda. And that helps by 10%, right? So we got rid of a line or two of boilerplate code, but basically that bulk of custom logic inside the comparator itself is the same, and it suffers from all the same problems. And unfortunately, I don't have time to go through this in detail, but you'll have to believe me that this code is the equivalent of the code on the previous slide. And so what we do is there's a new method called comparator.comparing, and it takes what we call a key extractor. So in this case, it's get last name. It's just a function, or it's just a method that gets a field out of your object. But what's interesting is a typical comparator is highly stylized code. I want to get the field from this object, and I want to get the field from this object, and then compare them. And so instead of writing that out by hand, comparator.comparing does that for you. And so you just say which field you want. I want to get the last name. Okay, boom, there's a comparator that compares last name. There's another method on comparator called then comparing. And so if I have a comparator, and this first comparator, the result of calling the first comparator is that the values are equal, then I want to apply a second level sort, and that's what then comparing does. So it takes two comparators and smashes them together in this particular way to give you a two-level sort. And so instead of having a bunch of conditional logic that does that for you, it allows you to build up this composite comparator from smaller comparators. And then nulls first is kind of the same thing. So generally we want to do a string comparison, but what if the string is null? Well, you're going to get a null pointer exception. Well, nulls first is another utility method that says, okay, I'm going to do a comparison, and I want to sort nulls first. So it sets those aside, and then for non-null things, it just calls the regular comparator. So again, the flavor here is that we're building up a complex comparator with lots of weird conditionals and stuff that you saw on the previous slide by composing little bits of pieces. So we start with a natural order, we sort the nulls first, and then we're sorting the results of first name on that, and that's the second level comparison within the first level comparison of get last name. And so there's a lot of stuff going on in this code that that saves you the effort of writing all that complicated conditional logic on the previous slide. I should have put up this slide because this sort of explains it here. But anyway, this basically says what I just tried to explain. And so I'll make sure this slide deck gets posted, and so you can take a closer look at this afterwards. All right, so after this, now that's the end of the Java 8 segment, and I'm going to start talking about Java 9 now. All right. Okay, so what the little bit of history of what went into Java 9. There have been a couple efforts over the years in Java to add collection literals, and these have always been proposed as language enhancements. In Java 7, there was Project Coin, and one of the proposals that was entertained was to add collection literals, and some proposals were floated around, but that never went anywhere. After Java 8, there was a JEP, JDK enhancement proposal. It was a little odd. It was a research JEP, but basically the idea was to scope out what was required to add collection literals to the language. And the result of that was a decision that we would not add collection literals to the language. And I think the most succinct way to explain that decision is to observe that unlike many other languages and systems, Java has clearly defined architecture where the JVM is separate from the Java programming language, and the programming language is in turn separate from the libraries. And collections are a library construct. And so if you mix the idea of collections too closely into the programming language itself, then things get to be very uncomfortable. And so the question is, suppose we have a programming language syntax that creates a list. Okay, well, what list should that be? Should that be an array list? Well, array list is fine for many things, but suppose I wanted it to be immutable. Suppose I wanted it to be sparse, or suppose I wanted it to be something else. And so it wouldn't be too difficult to do something simplistic in the language, but then that would bind too tightly to particular implementations in the library. And so if we didn't want that tight binding, then we'd have to design a programming language that somehow had a looser coupling with the library, maybe ended up calling collections builders or something. But basically, since the language and the library are architecturally distinct, building something like collection literals across that turns out to be a great amount of effort if we want to preserve the flexibility of keeping the collections framework at arm's length from the programming language. So anyway, so the upshot of that is we decided not to add collection literals to the language. And instead, what we said was, let's add some convenience APIs to the existing collections framework, and that will get us probably 80% of the benefit of collection literals, but it's much, much simpler to do, right? It's a library-only construct, so it's just APIs. We didn't have to make any changes to the JVM or the programming language or the compiler or anything. They're just new library APIs. And they're pretty useful. There are a few cases where it would be nice to have language support for it, but I'll talk about those in a minute. But otherwise, I think it came out pretty well, and they're quite useful, and I think you'll like them. All right, so the design goals for basically, so they're convenience APIs, and basically they're all static factory methods. So we are adding static methods to the interfaces to produce collections instances. So the main goals of these new APIs are convenience and brevity, to be as close as possible to collection literals as possible. But we wanted them to be space efficient. You can gain some space efficiency if you have an immutable collection. Since it doesn't need to be modified, you can pack things in a different way and save a lot of space. And also, the collections instances returned are actually immutable, which is kind of a new thing in the JDK. All right, so anyway, so JDK 9 is work in progress. This work was integrated quite some time ago, so any recent build of JDK 9 will have these in it. And so I encourage you to download JDK 9 and try them out. But the interesting thing about this is on its surface, adding these APIs, it's like, well, gee, you know, with an hour's thought, you could write out the APIs and implementations. And I think I did so. In fact, I did so several times. But what was interesting was that there are a surprising number of issues lurking under the surface and design decisions that we had to go through. So that's what the rest of this talk is about. So quickly, here is the overview of the new APIs in JDK 9. So there is list.of, taking 0, 1, 2, actually up to 10 arguments, and then list.of taking varargs. So that will create a list with however many elements you pass. There's set.of, which is the same thing. There's also map.of, and map is different because it doesn't take elements of a single type. Instead, it has to take key value pairs. So for a small number of key value pairs, we pass alternating keys and values. But if you want more than, and there's no way to do a varargs for that. So if you want more of that, we've added a new method, map.ofEntries. All right, so for efficiency reasons, so this is a snapshot of the Java doc for the map interface. So for efficiency reasons, we've provided 0 through 10 fixed arg overloads, because varargs unavoidably has an overhead of constructing and copying elements into an array. And so in order to avoid that, we provide fixed arg overloads. And so I don't know how many of you were here at the opening keynote when Chet Haas gave his technology business talk. I thought he was pretty funny. I would like to be as funny as Chet was, but I'm still working on it. But I think I have potential, because when I posted this API to Reddit, somebody said, "Is this a joke?" So anyway, here are some examples of the new APIs in action. In Java 8, actually this is kind of 3 examples glommed together. there's list, set, and map. And so if you needed to create a list, arrays.as list isn't too bad. If you needed to create a hash set containing specific things, well, the easiest thing was to create a list and then put it into a hash set. And then map, I think, is the worst. You had to create a map and then call put successively into it. And on the bottom, you can see on Java 9, you can say list.of, set.of, and map.of, and it's all right there, and it's pretty nice. So, so there's a variation here, which is if you wanted to create a map with an arbitrary number of pairs, then you have to switch over to this map.ofEntries method, which takes a varargs parameter of map entries. And so creating a map entry is can be kind of complicated because there's a map. The most common implementation of map entry is abstract map.simpleImmutableEntry, which is quite a mouthful. So one of the other things that this adds is a static factory method called map.entry, lowercase entry, that just takes two arguments, a key and a value, and returns a map entry instance. And so here's an example of that, because this exceeds the fixed arg variation, the fixed arg overloads of map.of. So we have to use map.ofEntries and then pass it, a succession of entry objects. All right, so there are a bunch of design and implementation issues that I alluded to earlier, and so I'm going to step through these pretty quickly here in the time remaining. So handling an arbitrary number of mappings is what I just talked about. We ended up at that solution after considering about 15 other alternatives. I should write those up sometime. Those are interesting. They all have pros and cons, but when you're faced with a lot of choices, you can't just look at them and say, I like this one better than that one. So I actually did come up with a set of criteria for what I wanted out of this API. And so obviously simpler is better, less boilerplate. But an interesting one is the API should be compile time type safe. So some of the alternatives that people proposed, if you have keys and values of different types, then the most common supertype might be object. And so how do you, and you can't have a varargs that has different types. And so some people said, oh, just take a varargs of object, and yeah, we'll deal with type unsafety, that's okay. It's like, well, I don't think so. Java is very much focused on static type checking at compile time. So having arguments that are not checked at compile time is kind of a dodgy thing to do. So another thing is we wanted the number of elements to be known at compile time. And so you can have an alternative was to have a builder. So you just call build, add, or something like that. And the problem there is you have to, in the process of building, you have to accumulate those. And that could involve successive reallocations and copies, because you don't know how many times the guy is going to add entries before building the final map. And so what we wanted to do is, again, at compile time, have the size be statically known. Or at least not statically known, but known at the initial entry. And so varargs does have that, because when you receive a varargs parameter, you get an array of a fixed size. And so you know that that's the number of elements you have. So another common one, somebody said, oh, just have two arrays of different things. And that's fine. Two arrays of different types, an array of keys and an array of values. And that's fine, that kind of works. You have to do some cross-checking to make sure that the arrays are the same size. But when you write out code that does that, then the keys and the values, unless you contort your source code in a very strange way, your keys are going to be very far away from the corresponding values. And so it's like, yes, you can do that functionally in the API, but when you write source code, it's just not going to work. So anyway, and then ideally, we would like to avoid boxing where possible. And it turns out that we were able to satisfy all of those except boxing. So I went over this already. There's a new convenience method called entry, which takes a key and a value. You can pass a succession of those to the map.ofEntries method. So that's what we ended up with. It's not perfect. It's a little bit more verbose than I would like, but I think it does satisfy most of the criteria, and it works well. All right, so here's something fairly new in the Java world, which is immutable data structures. So the instances returned by these new methods are immutable, which means that you cannot modify them. So I want to stress that this is what I guess I would call conventional immutability. So it's just like a regular Java collection. It's just that if you call a mutator method like add or put, then that is rejected with an unsported operation exception. I want to contrast that with other libraries and other language systems that have persistent or immutable persistent data structures, where you can sort of modify the data structure, but what you get is a new data structure that has sharing with the old one. That is not what this is. This is kind of conventional immutability. Anyway, this is good because there are a lot of cases where people could use immutable data structures if they had them in Java. And so it's a very common case to initialize a table of things or list or something at the beginning of a program and never change it for the lifetime of the program. And so you don't want those accidentally being changed. And if there's a space-efficient way to store them, then you want to do that because if you know that the structure is never going to be changed, then why pay a space penalty for the flexibility of potentially modifying the data if you're never going to do that? So there historically have been unmodifiable wrappers in the collections framework, and that's kind of the closest thing to general purpose immutability that was there up until now. So what you had to do was create a mutable data structure, populate it, and then wrap it in an unmodifiable wrapper. And so that sort of gives you, and then throw away the reference to the underlying one. And that sort of gives you immutability, as long as you remember to throw away the underlying reference. But unmodifiable is actually a different concept. The idea of the unmodifiable wrappers is that they are views onto another collection that do not permit modification. But if you still have a handle on the underlying collection, then you can modify that. So if you call into somewhere and it gives you an unmodifiable view, that means you can't modify it, but you cannot trust that it will never change. So, because somebody else might be modifying it. So this idea of unmodifiable that already exists in the collections framework really is different from immutability. And so these collections cannot be modified unless you go in like with reflection or unsafe or something like that. There are no APIs that modify these collections. All right, so here's an interesting wrinkle that bears some explanation. The iteration order of the hashed set and map implementations that are returned by the new collection factories. The iteration order is randomized, and it literally is randomized. Now, if you look at sets and maps in the existing collections framework, then there's some words in there about the iteration order is unspecified. But historically, the iteration order has been pretty stable. So if you iterate over the same collection multiple times, it'll be in the same order. Even from run to run, or even from JDK release to JDK release, if you put the same elements into a hash map or a hash set, they'll probably come out in the same order. And the problem is that a lot of code grows to depend on very stable iteration order. And from time to time, something will happen that will change the iteration order. Like if your program gets different input, it might cause the hash set to the hash set or hash map to rehash everything, and then things will come out in a different order, and your program will break. Or in the JDK, sometimes we've had to make some performance enhancements or fix security vulnerabilities or something where we would change the iteration order of a hash map. And people yell at us a lot when you did that because you broke our code. It's like, well, we come back with a finger wag. Yeah, you're not supposed to depend on the iteration order. But we can't take that line too hard because when we change the iteration of hash map, our own code breaks, right? And so what happens is it's like, oh, where's the iteration order dependency in this code? I don't know where it is. Just change it to a linked hash map. That'll give us stable iteration order. And then the problems go away. And it's like, so that's really uncomfortable. But the fact is, we have the worst of, prior to Java 9, we have the worst of both worlds. We have iteration order that is unspecified, but that is stable enough to lull people into thinking that it actually is stable. And then when it changes, lots of stuff breaks. So the solution to that, for the new collections only, is that the iteration order is randomized. So what happens is at VM launch, basically it gets a random number which is XORed into the hash code. And so the effect is that from one run of the JVM to the next, the iteration order of the set and maps returned by the new factories, the iteration order will change from one JVM run to the next. And so the hope is that this will flush out any code that has latent dependencies on iteration order, and that those problems will be flushed out during development and testing, and so that they won't come out in production. But also, actually, it's also buying ourselves some flexibility here, which is we may want to go in and reorganize the internals of the way that entries are stored in these maps or sets. And we want the freedom to be able to do that and get you, better performance, better space efficiency, and so forth, without having to worry about preserving iteration order. So that's one of the toughest things. If you have to preserve iteration order, that's a cost that needs to be paid, even if it's not actually specified. And so we wanted to avoid that. So again, this applies only to the new collections returned by the new collections factory methods. The existing collections, those are going to stay the same. I think adding randomized iteration to those, randomized iteration order to the existing collections is not something that, certainly not something we're going to do by default. Maybe there would be an opt-in thing for debugging purposes, but nothing more than that. Okay, another characteristic of the new collections is that nulls are disallowed. I think in retrospect, the new collections introduced, when the collections framework was originally introduced back in 1.2, the main collections did allow nulls, and in retrospect, that's been regarded as a mistake. Nothing recent has allowed nulls. In particular, none of the concurrent collections allow null entries. And there are a couple of reasons for that. One is null shows up in special places in the APIs. So there's the case of map.get. If that returns null, does that mean the entry is absent? Or does it mean the entry was present, but its value is null? So you have to do something else to disambiguate. But there are also some things in the, especially in concurrent collections, like map.compute, like I mentioned before, if your lambda expression returns null, that has the effect of removing the entry, as opposed to storing a null into the map. And so null is a very important special case that's useful for APIs in that way. Also, it's really useful to have nulls inside a collection as special sentinels. And so it makes, if you actually look at what things like hash map, the regular old Java util hash map has to have a bunch of special cases in case somebody wants to store a null in the hash map, because by default, null means there's nothing there. And so there's special cases sprinkled throughout the code, and it just makes things more complicated and error prone. All right, so another wrinkle here is that when you're populating a set or a map, it throws exceptions on duplicate entries. And there's a bit of rationale here. I think I need to move on a little more quickly. But if you have a big table like this, here's an example. There's a duplicate entry in here. And I think either, most systems use last one wins, which means that if you put this, if you compile this into your program, you would actually have one fewer entry than you expected, and you'd have some weird behavior at runtime. But if you actually put this into Java 9, it will throw an illegal argument exception and say that, well, hey, this is a duplicate entry. And so the point here is that this is a library API that is modeling collection literals. So if you have a collection literal, that means you're writing out all the values. And so if you put in duplicates, that's probably an error. I'm very sorry about this. I'm running short on time. So I have a bunch of stuff to say about space efficiency, but really the existing, I just want to say very briefly, the existing collections, especially things like HashSet, are pretty space inefficient. They use lots of objects and lots of pointers to different objects. And so if you put a couple entries into a hash set, it takes 152 bytes to represent a hash set with 2 entries. And so the new set implementation is much more compact. So if you have a new immutable set with 2 entries, it only takes 20 bytes instead of 152 bytes. So once again, I will have to skip beyond this. There are a couple things of design rationale here. I'll post these slides on the web so that you can see them, and I'll also be available for questions afterwards. But I'll just move directly on to my summary here. So the collections framework is 19 years old, and it's old, but we're still working on it. There are lots of new enhancements in Java 8. We saw all those new default methods that add new functionality to all the existing collections. And then in Java 9, we have our collections convenience factories that provide new, compact, immutable collections, and they're much more convenient to write. And I encourage you to go to the JDK9 download page and download JDK9. They should be in any recent build, and I encourage you to try them out. So thank you. I'm sorry I don't think I have time for questions, but I'll be available afterwards for a conversation. Thank you.